So ready to go, but I just realized I forgot something. So just to make sure that we're fully underway with the first Rapids conference, I have something. If you could hold that. I'm not entirely sure how this works. There we go.
I just wanted to, my name's Luke, and this is Stephen, who'll introduce himself in a second. The first thing I wanted to say was thank you all for coming. The second thing I wanted to say was thank you to the Dotmesh team who made this happen. So could you please put your hands up? And I'd like just a round of applause for everyone who made this event happen, please. Thank you. It's the first time we've run an event, so thank you for being our guinea pigs. And the other thing I wanted to mention was please tweet. We can amplify the message of solving reproducibility and provenance in data science by tweeting. And so if you could please use the hashtag Rapids2018 that's in the corner of every slide, then that would be awesome. Thank you. And so over to Steve.
Cheers, Luke. You guys can hear me, yeah? So everything Luke just said, thanks to the Dotmesh guys for today and giving us the opportunity to kind of get together and start talking about reproducibility and provenance, well, properly almost. So I'm Steve. I'm a bioinformatician. I was rebranded as a data scientist like everybody else, and I work down at King's College London and the University College London with the departments of biostats and health informatics and Institute of Health Informatics. And we're affiliated with two biomedical research councils. These are departments that are embedded within universities and affiliated with hospitals where we do a lot of translational research. And it's all dealing with health data, patient data from the NHS and also as part of research. And now we're part of something called the Health Data Research UK. So our broad interest, I'm going to keep this very brief, is basically from bench to bedside via the computer. So we will take data generated by research labs and also from within the clinics, do fancy maths and data science and bioinformatics on it, and kind of the aim is to then get that back into the clinic with some actionable insights. And we're open to a lot of collaboration, open research, knowledge sharing, and there's aspects of the group that do lots of kind of DevOps, so software development and applying computer science to healthcare and clinical research. And the big thing too is personalized medicine and quantified self. And the quantified self here refers to, if everybody's got a Fitbit, there's a big movement now in kind of measuring everything we can real time on patients and individuals and feeding that back into healthcare via departments like ours and other institutes. So today we're here to talk about provenance and reproducibility, and I've got some kind of nice statements here that I want to use to set bits of the scene for today. And the first one is provenance is the missing feature in rigorous data science. Now, if you're here, you either don't know this or you really, really strongly agree with this, and I hope it's the latter. And one of the next big breakthroughs in analysis will be in the ability to combine, deploy, and maintain all of our existing maths and algorithms and workflows. And I'd like to add, and then put this under a fully reproducible way and under complete provenance. And this is kind of, I think, a dream for Luke and myself, people working with data in it currently. And what we mean by provenance, who's heard of provenance and reproducibility? Most people here. Who does it? Okay. So by provenance, basically we just mean something, the origin of something, right? So in our world, to track and document the source of our data and all the models that we apply to everything we do. And this is really, and it literally is the who, what, why, where, and when, and how of everything we do at every stage. Those little acronyms there. EDA, if you don't know, is exploratory data analysis. ETL is database stuff, extract, transform, load, and then all the reporting we do. And what we want to do with provenance is capture the dependency between data and also the dependency between every little step that we've done to generate our final result. And in the end, this is all good for reproducibility. It should be, it's good practice, and it should be best practice and enforced, and it really often isn't. And now under current climate, this is really, really good for GDPR. Who's heard of GDPR? Surprising, yeah. Now, why? So this is personal to me, and why is Rapids important to me? And it's largely to do with the current work that we're involved in and the institutes that we're involved in. This is HDR UK, and they got this grand claim of here, which they're going to do is making a game-changing improvement to health of patients and populations. And just quickly, part of that's broken down into 4 little kind of domains, and the big things here are actionable health data analytics, and then precision medicine. I'm not going to go through all these slides here. And what we want to do then is modernize public health. So these are universities and hospitals up and down the country that are getting together to share their data and share their ways of working, and just make everything a lot better for us. In the end, aspects of that work is going to involve, this is the data sciencey bit for HDR UK. Measure everything we can on patients, stick it in a big mega machine learning model or AI, and predict something. Predict their outcome, predict death, predict prognosis. There's some sniggers there. It'll happen if people start practicing kind of decent ways of working with reproducibility and provenance. And this is my world. So as a researcher, not just an academic, but as a researcher who's in the business of proper translational bioinformatics. So I'm not a career academic, and I got into this because in the end, it's all about the data, but it's all about the patient and family. So initiatives like Genomics England, where they're sequencing the DNA of 100,000 patients and looking at rare diseases and cancers, they've generated a mass amount of data, and at some point, it's already happening. That's being fed back into the clinic via labs like ours, and we're making a difference. We are helping patients get diagnoses for rare disorders. Cancer is going to be a bigger ask, but in the end, the diagram on your left, my left, that's what we do. Everything involves measuring something and recording it, and having data that we feed back to the clinician, the patients, and our other collaborators. And we don't do a very good job of that sometimes. Now, how I learned to stop worrying about version control, not stop worrying and love version control, is I made the transition from the lab. I was a molecular biologist, and then I became a bioinformatician, and that was literally, I wanted to learn how to deal with my data and analyze my data that I'm generating. And when you make that transition, the things that you discover, there's a lot of new ways of working and a lot of new ways of getting organized with data and just keeping track of everything you do. And it was shameful, we still kind of do it, and you just discover all the rubbish that we do and still do that contribute to the reproducibility crisis. And this is something that is still happening. The public are aware, and we're getting better at it. So my new world, when I made that transition from the lab of doing things in a fairly messy way, I'll talk about that in a bit. I didn't know about Git. I didn't know about GitHub. I had no idea about READMEs. There's things like R and Python notebooks, and there was the whole community around people sharing code and sharing data, and now FAIR principles. And this is something that myself and the lab that we work for are subscribing to now, and that everybody should be subscribing to within our healthcare domain. So my old world was lab books. So back then, provenance and reproducibility were our lab books and our publications. And the data we generated kind of had a life of its own. It would sit on somebody's external hard drive and be shared or not. And lab books done properly do make reproducibility and provenance work. Right? So the idea there is you should record everything, and you'll have everything about the experiment there, your materials and methods, name, version. That will get signed off, double-checked, and I put in brackets there sometimes because it's not really enforced. And the level of detail that used to go into lab books, there was literally one-liners to prose. So there was no, and that was down to the way the labs worked back then. So we never really did formal version control, and this is all very personal here. So I'm confessing, and I know a lot of people here who are laughing. You probably have done the same thing. We lived in and still do live in a Microsoft world where everything was, if we didn't enter it directly in the lab book, it would be written down electronically in Word. We'd do things in Excel, PowerPoint, and then we'd cut and paste that into the lab book. And all of that will then get very, very heavily edited for publication. So the whole truth is not out there. It looks like it is, but the whole truth isn't there. And our analysis was all GUIs and things like SPSS, so we got very used to using pointy-clicky kind of software and creating plots in Excel. That was my old world. And we'd work iteratively and very quick, and we'd never record those steps properly, or the software versions. This is all stuff that I discovered when I made that transition. things that we should have been doing, that I should have been doing, that I wasn't doing, and it did cause a lot of headaches, and it still does. And our data would be just stored. We generate it, we stick it on local hard drives, have it on HPC if we're lucky enough, now bits of the cloud. And what's worse is sometimes that the documents we produce and the data we produce could be overwritten or lost. And then there's this. Now this, everybody here probably does this. I still do this. This is our hacky version control when we're working in kind of healthcare and life sciences right now. We've all got documents where we've got untitled or even various strings of version 1 to whatever with our shopping lists in there. And I'm confess I'm doing this to my PhD student right now, that final doc. So this is what we are dealing with and what we have to deal with. And we never really did, there was no formal version control model provenance that we did. And we, like I said, we tell a story, a very sweet story where we have raw data that's been generated. We do something to it in that gray box. We'll go through various versions. These are quality control steps. Or if this is a machine learning model, various parameter tuning steps that we go through to produce a final data set that we then use for publication. And this is a nice, sweet story that we would stick up there and get that published, and things that we would tell our supervisors too. And maybe not even show, tell our lab mates. So nobody ever knows the truth of it. Now this is reality. Again, anecdotal, and this is the truth. This is the tip of the iceberg. Think about that raw data almost, it exists virtually. It gets generated at some point. Each of those little nodes there you can take as a process or a postdoc or an RA or anybody that comes to the lab, takes that raw data, they do something with it, label it any which way they want, and then you'll see with the black nodes there, that's another postdoc that will come in and inherit another set of data from somebody, and they all generate the same file at the end. They'll all label it final. So that looks the same, labeled, but if you then dig into it, they're all very different. And that's why we have reproducibility issues there. And what's even worse, and this has happened one too many times, is a version of the final data set then gets, it becomes the initial, ground zero raw truth. That's the original data. And without things like GitHub, without things like provenance and reproducibility and tracking, or kind of better ways of working that will get enforced in labs, this is all too common. So we don't do it. We don't do it well enough, and it's not standard operating procedure, at least for every lab that I've been in. I've never gone in there and I've had the PI or the professor say, this is version control, this is what provenance is, this is what you want me to do, even down to, here's the format I want you to present your lab book in. And it's not just the lab-based people. So I gave a talk on GitHub to our Department of Biostats and Health Informatics. The informatics guys knew what GitHub was. The entire set of statisticians a couple of them have heard, none of them are using it. KCL went through a pretty nasty issue with hard drives going down and data being lost, and they didn't back up, scripts are lost. We can solve those issues with things like we're going to talk about today and what dotscience are putting out. And a lot of that down is to that's the world we live in, that's our culture, there's a lack of awareness, there's a lack of education. My thinking is every undergrad, even at school, should be taught basic principles of data science, and that's literally how you organize a data project, and what GitHub is, and what version control is. And I've said this before, it's not enforced in many labs. And there's currently within our world, there's no real incentive to have our ways of working aligned properly with rapids. There's a pressure to publish quickly, and things get turned around very, very quickly, and nobody keeps track of absolutely everything. Nobody wants to take that time. I was completely unaware of all these things until I made that transition. My supervisors are unaware. Largely the institutes are unaware of these things unless they're embedded within some kind of data world that have these current best practices up and running. Personally, the term provenance was never mentioned when I initially started out. Reproducibility and replication were just sexy catchphrases. There were things that that we're all aspiring for. And all this was supposed to be captured in our lab books and then in the publication. And it really was wishful thinking. That wasn't really the case. I mean, I got lazy with the lab books too, so I'm knee-deep in this and responsible for some of this too. And I'm a bit cynical, but the public are onto us. We'll share these slides, and there's some links here. Some of these articles are a couple of years old, but they still hold true. We're still very messy with what we do in academia. And not just academia, but probably a lot of the industries too. And the issues that we face in healthcare and research it's down to bad data management, and that can be fixed. And then there's bad practices. There's no data management. There's very little experimental design sometimes if you're working rapidly and you have to get things out quickly. And the analysis plans, they're works in progress when you start often. There's no formal bit of paper that says, we aim to do this, we're going to use these methods, we expect these results. That should be commonplace. And what happens in the end is we end up with false positives and spurious results. Translational research suffers, the patients suffer, and I'll be even more dramatic there. Patients could end up dying because we're missing out on things and not doing things as well as we could. And we waste a lot of money doing this, a lot of money and time. And then with GDPR, there are going to be serious legal, ethical, and implications coming up if people get caught. So the reproducibility crisis is not just in the fields of psychology and medicine where I live. AI is facing the same issues. And there's a nice article that's recently been published in Science you can have a look at, where he just points out a very, very quick thing that the AI folks and the computer folks in research are actually doing very similar things. We're not sharing code. We're not recording everything. And the assumption, and this is the assumption, these are some quotes from the paper, and this is a natural assumption I had, where if you do data and you're doing maths and you live in that world, because you have code, this stuff should be second nature. We should have reproducibility, we should have provenance, and it's not happening. And then there's lots of excuses that people come up with, and no time to document every hyperparameter. And we just had a chat just now at coffee where people say they don't have the time to document any of their code. They don't want to, it's laziness, or literally, you don't want to take that extra 5 or 10 minutes to do this properly so you can show your boss results and then write up a paper. And there's lots of common issues between all those worlds, the basic life science researchers and the computer science research world. One of the biggest issues, though, I find is actually that lack of awareness at all levels. So our bosses and our bosses' bosses aren't aware of it, and the people in the lab aren't aware of it. Without some kind of formal education, a formal, kind of handbook of best ways of working. And there's a lot of kind of ego that needs to be massaged, and people are scared, so they worry about being judged if they show everything. They worry about something new. There's also old dogs. They don't want to learn anything new. And there's fear of the command line. I made that transition. You just need to want to sit down and do it. And then there's laziness. I've had students, they're not here, who come towards the final year saying they wish they had done what I had suggested in year one with documenting things and organizing their folders and even signing up to GitHub. And that was part of unknown. That was also part of a general kind of, I don't want to. I have to do what now? So there's a need for reproducibility in provenance and data science, and there's a need for that in absolutely everything we do that touches data, or touches something that you need to record for somebody else to use or somebody else to come to in the future, and double check what you've done and to make sure we're what you said you've done, and we can reproduce those results. And one of the largest sources of error that we see in science and data science comes from kind of computing or recomputing results on different versions of the same data, and that different version is unknown. You don't know that sometimes. And then using different software versions. And then using different versions of the same algorithm. So, random forest implementation in 3 different languages you assume are doing the same thing. And we need to be aware of that. And then failing to capture and share all the steps you do when you're building your model. So who here actually has written in the code anywhere something that does capture all the hyperparameters that you've tested, the seed that you set at any time, the time of day? I didn't. I'll start doing it now properly. And we fail to capture the state of our data at each iteration of the analysis. We work quick in our world, sometimes too quick, and when we get involved in exploratory data analysis and looking at what the data is telling us, we'd be randomly generating plots and comparing everything with everything, and then we will forget to make a note of that, out of excitement or because we, lack of awareness and education. And the community is aware of this, and we're getting better at it, and there are solutions, and that's what we're here for today. to talk about some of those solutions that exist that are coming this way. And now I'll give you Luke. And he should be this one.
But I'm not. I'm all right, I've got this. Cool. Thank you very much, Steve. Really appreciate you helping us get this conference off the ground, and thank you for that great introduction to really the problem space. So my name's Luke Marsden. I'm the founder of Dotmesh. I've been working on solving storage problems in the DevOps and cloud native space for some time now. I worked on the first Docker volume plugin for connecting storage to containers, and I also work in the Kubernetes community. But we've recently started looking at reproducibility and provenance in data science, and we're working on a tool that should be able to help, that uses and builds on the shoulders of giants of the other tools that are available like Git and Docker and object storage in the cloud. So my understanding of how to make data science, AI, machine learning reproducible is that you need to pin down certain things. There are really 3 things that you need to pin down, at least, in order to be able to guarantee reproducibility of a piece of research or a model that you're developing and trying to ship into production. Now, the first one is the environment that the model is executing in. There's typically different versions of Python, for example, or RStudio, different versions of libraries, different runtime parameters will all play into affecting the result. Now, there might be bugs in one version of a library that you use in one version of the analysis that get fixed in a later version, and you don't notice that this is skewing your results. The second thing that you need to pin down is your code. Now, storing your code in Git or in another version control system is a great way to solve this, but it doesn't always align perfectly with the way that people do fast iterative data science. It doesn't always make sense to make a commit every time you change anything, and yet it's those fast iterations on code that result in things, in the results that you actually care about being generated, like the accuracy of a model. And so you need to pin down your code, and you also need to pin down the parameters that you specify in your code when you're training a neural network, for example. How deep is the neural network? How wide is it? And so on. And then the final one is that you need to pin down data, and you need to pin down the version of the data that you're using when you're training a model or when you're doing an analysis. So let's go through these one at a time and see how can you solve reproducibility for each of the environment, the code, and the data. Now, there are a lot of great tools out there. A lot of them are open source. The first one I'm going to talk about is Docker. So in the DevOps world where I come from, Docker has been a really big hit amongst software developers. And Docker is a tool for helping you pin down the execution environment that model training or any work that you're doing is happening in. The way that it works is that a Docker container is kind of like a tiny frozen runnable copy of your computer's file system. So if you imagine that normally on your computer you have Python installed, maybe with Anaconda, and you have certain Python libraries installed. Imagine the part of your computer where Python and all those Python libraries are. Now imagine taking that and freezing it and saying this is that version and naming it, and then you can always run against that exact version. And so Docker gives you the tool to do this. You can determine the exact version of all the dependencies of your code, and the mantra for Docker is that you can build, ship, and run exactly the same thing anywhere. So it means you can build a container image on your laptop, you can ship it, you can save it in a container registry, you can ship it to a cluster, you can run it in the cloud, and almost most importantly, someone else can pull it down later and run exactly the same bits that you used. And this is important because reproducibility often comes with a time delay. You want to reproduce something some time after someone else did it. And it would be natural to install the latest version of Python, the latest version of all the libraries, but you actually really want to pin down exactly the version that they were using at the time that they did the analysis. So this is important. We're going to do some workshops later this afternoon, and Docker is going to be, I think, the second workshop that we do. So in that workshop, you'll learn about Docker files. You'll learn about being able to declare the versions of things you want in the Docker file, how you can build a Docker image from a Docker file, not the other way around, and then push that image to the registry. And I won't go into all the detail about this now, but please stay for the afternoon, and my colleague Kai will be running the workshop on Docker. So now let's talk about code. So for decades, developers have been version controlling their code. If you go to any software development team these days and say, do you version control your code? Then they say, yeah, duh. But that doesn't necessarily translate to other fields like data science and medicine and this whole world of AI and machine learning, because Git is the most popular version control system, but it's kind of scary. It's a little bit intimidating when you first pick it up. It doesn't help that it was written by Linus Torvalds, who was the author of the Linux kernel, who is quite a sarcastic man. So the manual for it says things like Git, the stupid content tracker, as if you're meant to know what that means. And it's kind of scary, but it is worth persisting with Git or any version control system of your choice. Git is certainly the most popular one, and GitHub is sort of the de facto way that people share code, both publicly and privately. GitHub being a service online that you can use to push and pull your code to and from. But like I mentioned earlier, in data science, it's not always natural to commit every single time you change something while you're tuning parameters, but it's those results that you generate from those interim versions of the code with different parameters set and so on that you then copy and paste into your sort of virtual lab notebook. So it would be great if we could also sort of improve on Git and make it possible to capture those versions more frequently. Now, okay, so let's talk about data. So there's a couple of ways. There's two ways I'm going to talk about of pinning down the version of the data that you're using. And the first version is the first solution is just to be very, very organized. To have a meticulous folder structure. And I Googled for data science project folder structure, and I found this one from Microsoft. And I'm sure that people doing projects with data science have seen similar things, that maybe your supervisor recommends that you should organize your folder structure in a certain way, or maybe this is just something that you develop over time personally as you're working on a project, and you start out with Untitled 1, Untitled 2, Final, and then you realize that you've hurt yourself later by not being able to find a version of the data that you needed. And so you become more organized over time. And this is sort of the incumbent way of dealing with data. A similar approach to this is with, so when you're storing data in the cloud, I've spoken to some of the more advanced companies who are doing data management and doing data science on large data sets, and they have what they call an immutable data lake. And so this is this idea that you store everything in S3, for example, in object storage in the cloud. It's like a big, I'll talk about it in a second. But you never modify anything. That's what I mean by immutable. It's unchangeable. So every time new data comes in, it just gets sort of appended. And then you can always sort of point to a range of your files and say, these will never change. And that's a great way of achieving reproducibility. But what I see in practice is that people just don't do that. People do overwrite files. People, especially when they're in the sort of early iterative phase of doing work, it's much more common to overwrite files in place. So if you are overwriting files in place, then there is some technology that can help you track what you're doing anyway, which is versioned S3 buckets. So S3 is a scalable file system on Amazon Web Services. It's a little bit unfair that I just refer to it as S3 because object storage is also available from other vendors. So you can get Google Cloud Storage from Google, and you can get Azure Blob something. I don't know why they called it Blob. But Azure from Microsoft have a service called Azure Blob Store. And all three of them support versioned buckets. Annoyingly, they all support versioned buckets in slightly different ways with slightly different semantics. But the idea here is that when you, so S3 is a file system that runs in the cloud, and you can use an API to put files in it and then later get files from it. And there's a toggle that you can turn on for a bucket that not that many people know about, which is that you can say enable versioning for this bucket. And what that means is that every time you write a file, it gets a version number. And if you overwrite that file with a new version of that file, then it gets a new version number. And it's kind of like a stack, like in this diagram that I copied from the AWS docs. So photo.gif starts out at one version ID, and then another version ID, and so on. And this means that you can always go back and get to an older version. But the problem with this is that S3 is really a primitive. It's really sort of a building block that you build other systems out of, and it's not very intuitive to use it. You can use it from your Jupyter notebooks using the sort of Python S3 API, and they do have a file browser in the Amazon Web Services console, but it's not the most user-friendly thing in the world. And when you run an experiment in your notebook, it's not natural to write down the exact object versions that you were operating on. And what's more, you care about the version of the whole bucket normally, because you're sort of saying, like, all my data files, I care about this version of them, rather than this version was at that this file was at that version, and so on. So ideally, we'd have a way of versioning whole buckets, but S3 doesn't have such a notion. So that's reproducibility. I've covered sort of three systems that we can use to do more reproducible research. And I recommend that everyone learns about these things and tries them today. And we're going to have, like I say, workshops on Docker and Git. Didn't have time for an S3 workshop, but maybe next year. And these three things can help you get more reproducible research, but it requires work and it requires attention and focus. And as Steve was saying, those things are in short supply when you're rushing to try and get a paper out or rushing to try and deploy a new version of an algorithm in production. OK, so let's talk about provenance. In order to pin down provenance, you need to pin down the relationship between things. So far, I've just talked about the versions of things. But now let's talk about relationships between things. So if you have some data that you have sort of data A and data B, then you might want to start by combining two data sets into one. That might be the first step of your data wrangling process. So in the example I'll use in a minute, we'll have two sets of property data from two Bay Area estate agents, or real estate, realtors, I think they call them. And so you might want to combine data A and data B into data C. And then you might want to say, well, this data C is the canonical combined data that I'm going to run all my experiments on. And so what you have, and this is just sort of very basic computer science, programs take input and produce output. So every time this code is running to combine these two CSV files, for example, into this larger CSV file, data A, then this is sort of implicitly forming a provenance graph, whether you care about it or not. Now, the thing is that you normally can't see the provenance graph. It's normally something that's happening sort of as you do it, and it's hard to go back later and say, well, where did that file come from? And so losing the history of this provenance is really the problem here. And then, so there's another piece of code that's then potentially building a model to predict house prices based on, let's say, the number of bathrooms in the property or the square footage. And you might run that code, or different versions of that code, multiple times on the first piece of data to generate two different models. And those models might have different accuracy scores, for example. So the idea here is, well, how can we track this provenance graph? The point is, you want to be able to say, for any artifact in the graph, either a version of the data or a version of the code or a version of the model that you're generating, you want to point to it and say, show me exactly where this came from. show me the exact version of the tool that was used to generate it. Show me the exact version of all the Python dependencies that were used when this process was run. And show me the transitive closure of that, which is just a fancy way of saying, like, don't just show me the most recent thing, but show me the whole graph. So show me the history of the thing that created this and show me the history of that. So if basically the output data of one process will be the input data for another, and that will go back through this whole sort of graph structure. And there are tools out there that can do this. So there's a project called CWL, which I believe allows you to explicitly define a pipeline, and then you can run the pipeline, and then everything is captured. And there's another tool called Pachyderm that also allows you to do this, that allows you to build an explicit data pipeline. The issue that I have with these tools is just that they force you to define the pipeline up front. So you have to write some JSON code, well, some JSON text to define the structure of the pipeline, but you might not know what the pipeline is up front. You actually normally are figuring out the shape of the pipeline as you go by doing the work. And there's a sad fact as well, which is, I think we sort of heard this a little bit from Steve's comments. People don't care about reproducibility and provenance as much as they care about their day-to-day work. This is because, my theory is that this is because humans have a problem with deferred gratification. So when you're trying to achieve, the reasons to achieve reproducibility and provenance are so that you can come back to something later, or that someone else can come back to something later. And the key word there is later. It's not going to help you right this second. It might help you in an hour or a week, or it might help someone else on the other side of the planet in a year to redo your work. But it's actually not your top priority compared to getting a paper published or shipping an optimized model into production. So what I think we should try and do is find ways of introducing reproducibility and provenance to people while also helping them get work done faster and more accurately, and helping people to collaborate better with their team. And so I propose, or we propose at dotscience, that in addition to tracking reproducibility and provenance, that tools that do this should also help you track summary statistics. And thanks to Kate at the back, who came up with this idea. The idea here is that when we spoke to dozens and dozens of data science teams that we were speaking to when we were looking at data science as a market opportunity, we asked them to describe their pain points. And there was really one problem that stood out from a lot of those conversations. We asked them, how do you track the progress or performance or results of your models? And we got a range of answers. One of the answers was, we don't. We're flying blind. Another one was that this came up a few times, that we track it in a Google spreadsheet. And that's fine, but you're manually copying and pasting things into your Google spreadsheet that sort of refer to sort of short strings that refer to a specific bit of code or a specific version of the data. But you have to manually keep that spreadsheet up to date. We heard one person say that they don't have a system for tracking sort of the accuracy of their models. They just keep their teams really, really small. And, and this means that and they keep them in the same building. So in this case, you say, well, what accuracy did we get last week? Well, I think it was 97%. And I think Bob got it. And Bob's here, that's lucky. So we can ask him how he did it. And hopefully, Bob's laptop didn't get left on the tube, because that's where the version of the data is as well. And we'll get fired if we commit the data to Git, by the way. So that was an interesting conversation. And when we had that conversation, I mean, the person I was speaking to, they kind of knew that it wasn't the best answer. So ideally, we can integrate summary statistics tracking, i.e. the accuracy of a model, and also the parameters that are used to generate those models into a solution for this so that we can solve reproducibility and provenance and summary stats tracking in one go. So that leads me on to talking about what we're working on with dotscience. If only this was all a little bit easier. We've pulled together this event so that we can get your feedback on a new approach that we're trying. Really, we're putting this event on to start a conversation with all of you about better ways of doing this and how we can develop better solutions. So we're proposing a new system called dotscience, which pulls together all of the things I've described. It pulls together tracking the environment and all your Python dependencies or your RStudio or your R dependencies in Docker. It tracks data and integrates with version des3 buckets to do that work for you so that you don't have to figure out building a system to sort of integrate this primitive into something that you're working on. And it also uses the Dotmesh file system. And I won't talk in great detail about this today, but in short, Dotmesh is a system for being able to very efficiently snapshot and clone versions of data sets and versions of workspaces, and workspaces have code in them. So Dotmesh is again, it's another primitive. It's one that we've developed that we're putting into this product so that we can make it easier and faster to track everything. So it also tracks code versions, and it tracks code versions which generate summary statistics. It currently integrates with Jupyter, and we're working on RStudio support and support for scripts. Just as a quick show of hands, who here uses Jupyter in their day-to-day work? Lots of Jupyter users. R? Interesting, a lot of the same hands went up. And who just writes scripts? There's no shame. Great. Cool. So the other thing that dotscience does is it builds this provenance graph on the fly. So for any data set, it allows you to see which code generated it as the output of which other code, and it captures the versions of everything. And the same for any model, because models are really just another type of data. It also solves this summary statistics tracking. So it builds this table and it builds a chart, which I'll show you, of every run that generates some error rate as a function of the parameters, for example. And it keeps together the version data set, the version model, all the model parameters, and the environment, so that you can track all of them over time. And the idea is that this is meant to make it faster to do your work, not slower. So rather than introducing more steps to your workflow to achieve reproducibility and provenance, it actually makes it easier by giving you visibility into like what parameter you might want to try next. And giving you the ability to sort of slice and dice different results and get insight into your parameters and which data sets give you different results. So I'm now going to attempt to do a live demo. So could you all please pray to the demo gods for me? Right. So I have here this tool that we're working on. And hopefully you can see that okay. So the idea is that this is a native app that runs on Windows and Linux and Mac. So it depends only on having Docker installed. And then it's just a matter of clicking some buttons to get started. One of the things I'll point out is that there's a work share set up here. And inside that work share, or that workspace, you can see there are some files. So I've got a couple of IPython notebooks, and I've got some CSV files. So if I open up the CSV file, you can see here's the property data from one of my Bay Area estate agents. And here's some other property data from a different Bay Area estate agent. And so we're going to build that model that I talked about earlier, where we predict the price of houses based on various features. And this is the same example that you'll all get to try yourselves in the workshop this afternoon. So this is really just a quick preview of the workshop. And so what we're going to see is that, so if I just click this button, oh yeah, so I need to install Jupyter. There's a button here for installing Jupyter, and that's going to install a version of Jupyter that has TensorFlow and scikit-learn baked into it. And then that version of Jupyter with those Python dependencies get versioned together because they're in a Docker image. So it's launching them in Docker on your machine. So what we can see here is, I'm just going to make this a little bit bigger. So I'm going to show you two things side by side. The first one is the Jupyter interface, and the second one is the UI that we're developing to make it easier to see what you're doing as you're doing it. So hopefully this will all work at this Zoom level. So let's take a look. So we're inside Jupyter here. A lot of people in the room are familiar with Jupyter, so none of this should come as a surprise. We've got a couple of notebooks, we've got some data wrangling, and then we've got a linear regression model that we're going to build. And like I saw just on my Mac just now, we've also got these CSV files inside these agent 1 and agent 2 directories. So the very first thing we're going to do, oh, and by the way, there's also a dotscience tab that you should be able to see in the top left, and that's new. And it currently shows you that there's no commits. That means there's no versions of runs that have been captured yet. So yeah, the very first thing we're going to do is do some data wrangling. This notebook simply reads two CSV files, the agent 1 and agent 2 CSVs. It randomizes them, it describes the data. I mean, let's just run it as we go. So it's reading in those CSV files. It's randomizing them with a random seed, and that's something that you want to fix as a parameter. Otherwise, you get different results every time you run this. And then we can just do describe on the data frame, and it shows us that we have sensible-looking property data. Seems pretty reasonable. Like that looks fine. We then drop some columns that we don't need. This is sort of data wrangling that we might do just as part of our normal day-to-day work. And we check that whether there's any nulls in the data, and it looks like there aren't any. So the data looks clean at first glance. I mean, we might find some anomalies in it later, but let's save it out as at this version and say this is good enough to start with. So what we're doing here is we're saving out that property data to this combined housing data file. And then we tell dotscience that we've done it. And so the first thing you'll notice is that there's now a version that's showed up. So there's a version that shows how many rows were processed, because that's the summary statistic that we wrote out. And the other thing is over here in this view here, you can now see that the provenance graph is forming. So because we told dotscience that this version of the code was going to read from this data set and this data set and then write to this data set, we were able to start forming this provenance graph. And in doing that, we've snapshotted exactly the versions of all of these things that were running at that time. But we haven't got any runs yet because we haven't trained any models yet. So let's go ahead and do a model. So we're going to do a simple linear regression. We're going to tell dotscience that we're reading from the combined house data and writing out to a model. And then we read in the combined house data. And then we do some plots just to check that our data looks sensible. So we're plotting square footage against the price, bathrooms, bedrooms, and total rooms. And you can see the data looks a little bit like this. So it seems from this data like it might be plausible to run a linear regression against this to get an estimation of the price. So we're going to start out with the simplest possible linear regression. We're just going to, looks like the square footage might work. So we then split the data into a training set and a test set. We run a prediction and then score it. And we get some results. So these statistics that come out of testing the trained model are important because we care about these statistics. The error score, for example, is the score that we want to tell our boss that we managed to get down, or collaborate with our team and say, well, that version on from last Thursday got this exact rate, this exact sort of accuracy. And then finally, we save that model to a model file so that it's stored and so that it can be used again later. So at that point, we know which feature we used. That was the parameter that we changed. And we know the error rate that we got out of it. And so as soon as we save this notebook, we now have another version that shows up. And it's automatically been captured. And the error rate in this case is 815K, so 815,000 US dollars. And you can now see that a run has shown up in the experiment tracker as well. So you can see this version, so you can see this exact version of the input data was run with these parameters and generated this output and generated this, this error rate as well. And so we also plot this on a scatter chart so that over time, you can see 34 seconds ago, this error rate was achieved. And then what's more, if you click on that, or if you click in on the run table as well, then you can see everything you need to ensure reproducibility of this result. You know who did it, when it was done, the parameters that were used, the summary statistics that were generated. We also need to add details about the Docker image that was used, so we have all the details about the environment in here. And you can see the exact version of the notebook as it was when the user hit save at the point at which they generated those summary statistics. So you can see all the graphs, and you can go in here and use this to actually go back in time to the exact version of everything. So you also capture the project files, the input data, and I think if I zoom out a little bit, then you can see the serialized pickle file is also here. Now, it might also make sense to be able to say, well, I want to deploy this model into production. So we're going to hook into later stages of the pipeline, possibly in this interface here. So I'll leave it there. There is a little bit more to the demo, but I'll save some of it for the workshop. That is dotscience. And like I said, this is really about trying to start a conversation and get feedback. So please, please come and talk to us. Give us feedback on this. Try it, kick the tires, break it. Yeah, we'd like to invite everyone here to join our beta program between now and October when we hope to launch. We'd like to get everyone involved. So yeah, you can try this yourself this afternoon. There's a roadmap, which I'm out of time to talk about, but I'm happy to talk through with people afterwards, and we'll make the slides available. And yeah, we need your help. And we have a picture of a kitten, so please help us. Oh, and finally, if you want to sign up for the beta, please write down these two links. Beta.dotscience.io will just take you to a form where you can say, I'm interested, I'd like to get involved. The deal is basically, if you're willing to give us some time and give us feedback on what we're working on, then hopefully we'll give you something that helps your work and makes data science more reproducible and provenanceable. And yeah, also join our Slack, so you can come and chat to us online at slack.dotscience.io. And that's it. Thank you.